All right, here we go. I haven't done this in a long time. Let's do it. Today we've got this beautiful problem, classical one. Anybody who is somebody and is doing some calculus has done this type of problem. It's called the Norman window. And the idea here is to optimize the amount of light by shaping it differently. This could be uh, a really thin window on the top, and then like this. Or it could be really big like this and then have a small rectangle on the bottom. Both of these shapes would be more or less similar to the one that's proposed. The idea here is that different shapes would let in different amounts of light, and we're trying to maximize it. To make it just a little bit more interesting, we've got this added fact here that the top part is tinted, so that only 15% of the light goes in there, meaning that only 15% of the area counts. More or less 85% of it, you can think about it as being blocked, 85% of the area on the semicircle on top. So that adds just a little bit of challenge to that just to make it perfect. Roughly speaking, on all these optimization questions, um, let's see here, let's put this aside for a second. On all these optimization questions, roughly speaking, the steps are going to go like this. First of all, we're going to define exactly it is that we're trying to maximize, okay? You can't fix a problem if you can't put a name onto that problem. So we're first going to put a name onto it. What are we trying to maximize or minimize? Second step is we'd like to find a formula for whatever it is that we're trying to maximize or minimize. Third step, once we've got the formula, often those formulas will have more than one variable. This is not third semester calculus, this is first semester, so we're trying to just take the one variable on the independent side. And so we'd like to eliminate all but one variable on that formula that we get from step two. And then once you do that, then you're off to just finding the extrema, which involves finding the critical points. Roughly, there are two types of critical points. Points where the derivative is zero, points where the derivative doesn't exist. And lastly, we'll classify all the critical points that we have. These critical points that we find, these are our candidates. We'll make a little table here. We'll place them on there, and we'll figure out which one lets in the most amount of light. Capiche? All right, talk is cheap. First of all, what are we trying to maximize? You read the problem, read it a few times if you need to, but basically, greatest possible amount of light. So I'm trying to maximize light, and that takes care of my first step. I'm trying to maximize light. So we can give it a name here. We're going to call the function for the amount of light, we're going to call that L. I need a formula for L. The amount of light would be equal to the amount of light that comes in through this guy plus the amount of light that comes in through that. Now, it's important here to note that light is almost the amount of area, except for it's not. So I'm going to make sure that I'm not talking about the area here. I'm talking about the light. How much light is coming in through these ones? Well, that still doesn't look like a formula, but I can keep making small changes here. The amount of light that's coming in there would be almost the same as the amount of area, except it's not. It's the area times 15%. Plus the amount of area here, that would be more representative of the amount of light. Okay, that's its area. And so what would be the amount of area here? Well, the area would be pi r square if we were talking about the whole circle, but we're not talking about the whole circle. We're only talking about half of it. And so since this is only half of it, I'm going to say half of the area of a circle. And then, of course, don't forget I'm multiplying times 15 over 100 to turn it into a percentage to take care of this idea that allows only 15% of the light in that entire area. So that's the computation for that part. The area here, I'm going to call this a base. I'm going to call this a height. So the area there would be base times height. So I could simplify this just a tiny bit, and I could say that the amount of light is equal to a half. Well, I could multiply that half times 100 or 15 over 100. So maybe we can call that 15 over 200 times pi times r square plus base times height. Now I know you could go on and you simplify this, but as you know, simplifying is for the birds, and I ain't no bird. All right, that takes care of my second step, getting a formula for what it is that we're trying to optimize. The light, it's a more or less decent formula, except for we got some issues here. If you count the number of variables, here I can see a variable. We got R, we got B, we got H. That's too many variables. That's three of them. Now, like I said, you may have fun with some of this stuff in Calc 3, but this is Calc 1. We're trying to keep it to just one variable. So this part right here is super, super important. I want only one variable for the thing that we're trying to optimize. So I copy that formula over here, L, and that is equal to 15 over 200 pi r squared plus b times h. That's beautiful, but I want to eliminate some of those variables. Looking at the picture here, if we call this r here, this would be the base, this would be the height. I can see that this would also be r, and this distance would be 2r's, r plus r. And that distance should be the same as that one, 2r. So my b could be set to be 2r. It could be exchanged for 2 radii. So that tells me one way to simplify, to get rid of at least this b right here. That b could become 2r. That one right there could become 2r. And then if I count, I'll have r's, I have r's, and I still have h. I don't like this h here. We've got to get rid of that h somehow. So I'll go back to the function here. We're told that the entire perimeter is 5 feet. That's a constraint on how big this window can be. It can't be just any size it wants. It can't be the size of Minnesota, for example, because the radius is 5. And so let's look at that statement right here. The perimeter has to be 5. So the perimeter has to be equal to 5. Now the perimeter is also given by this side, which is b plus h plus the semicircle here. So plus that h again. So that would be equal to b plus h plus the semicircle. Let's leave it like that. Semicircle. That's this piece right here. And then plus another h, plus another h. So that takes care of my b plus h plus the semicircle plus the h. And we're back to the b. Look at that. I mixed symbols with letters. Nothing can stop me. So, and I'm adding them together. Yep. Beautiful. So now, the b, the base, that's equal to 2r. We know that. The h, I don't know what it is, but I can put together those two h's. So that's h. Now that would be the circumference of the circle is 2 pi r. If it was, that would be the case if it was an entire circle. But since it's not, it's only half of it, I'm going to slap a 1/2 on there so that I get the circumference or the perimeter for that portion of the window. So that means that the perimeter is equal to 2r plus 2h plus pi r. And we were told over here that the perimeter is equal to 5, so I could say 5 is equal to 2r plus 2h plus pi r. Now I can, remember, let's keep our eye on the ball. We were trying to solve for this guy right here, h, so that we could substitute and have only one variable. So if I could take this guy and substitute for h, I would get the following. 2h is equal to 5 minus 2r minus pi r. So that h is equal to 5 minus 2r minus pi r all over 2. You see why they pay me? I make this stuff look easy. So h is equal to 5 minus 2r minus pi r all over 2. So we get that the amount of light is equal to 15 over 200 pi r squared plus 2r times 5 minus 2r minus pi r all over 2, which you can reduce it just a little bit maybe if you want to clean it up. 15 over 200, and I know you could simplify that, but I'm way too sexy to simplify. So this gives me, I can cancel this r, or no, I could cancel this 2 here, and that would give me 5r minus 2r squared. What I'm doing here is I'm distributing that to that, that to that, and that to that. So that gives us all that. And look what we have. We have the thing that we're trying to maximize, the what, which is L, and we only have one variable. For our L depends on only one variable, and that is our R. There's no other variables on this. And that right there, that's a beautiful thing. Okay? And then we're done with step 3. Now, step 4 is we're going to try to find critical points. So critical points are points where either the derivative doesn't exist or the derivative is equal to 0. So either way, we should try to find a derivative. That might not be a bad thing to do. So I'm going to try to find L prime R. That would be the derivative of L with respect to R. So I'm looking at this formula right here, and I'm going to be doing, this is just a polynomial in R, so it's quite easy to find a derivative. So the first part would be 30 over 200. That would be pi R plus 5 minus 4 R minus 2 pi R. And find the places where that's equal to 0. So we set that equal to 0. L prime of R is equal to 0. That means that 0 is equal to 30 over 200 pi R plus 5 minus 4 R minus 2 pi R. That tells you that 4R minus plus 2 pi R minus 30 over 200 pi R is equal to 5. So I moved all the things that had an R on the other side, so that I get 4 plus 2 pi plus 30 over 200 times R is equal to 5. So I could just solve for R. This would tell me that R is equal to 5 divided by that entire coefficient, 4 plus 2 pi plus 30 all over 200. Okay. And when you try to run that through the calculator, that tells you R is approximately 0.51 or something like that. So that gives us one critical point. This is a degree 1 equation, so by fundamental theorem of algebra, you'd expect at most or exactly just one answer. Now we move on to the points where the derivative does not exist. Well, since the derivative is a polynomial, I'm going to be looking here to copy the derivative. I'm going to write the L prime of R, which is equal to 30 over 200 pi R plus 5 minus 4 R minus 2 pi R. That's a polynomial, exists for every real value of R. So therefore, there are no critical points of this type. And together, I've got a complete list of critical points. I've got a point here, well, a point here, and nothing here. So this is my entire list. And that takes us to the completion of step 4, finding all the critical points. I only found one. Last thing is we've put all our candidates on a little table here. R and the amount of light. So I only found one, which is approximately 0.51. I go on and calculate that. And the other possible R's are the endpoints. Extreme occur either at endpoints or critical points. So since this is the window and we're told that the perimeter is 5, there's no way that R could be bigger than 5 or even 2.5. So you could say as a boundary, R would be no less than 0, no bigger than 5. So I'd want to calculate the L for each one of these. How would I do that? I would go over here and I plug it into the L function here so that we can compute each one of them. Once we compute each one of them, we would put that here and here, and here, and then we would just observe here and find which ones are the extreme. I would just point out at the big one, at the biggest one, and that would be it. Now, just to make the math simple, or sorry, the algebra simple, because the calculator really bores me, and actually having to put these on the calculator, it's a bit tedious for me. So what I did is I put it on my favorite software, which is Sage Math, and I just copied it here. And so I got the light here. Notice how they actually the software will simplify the 200 or the 15 over 200, whatever it was. It'll simplify it. I went through all the steps. We substitute your B here into the L. The perimeter was set to be 5, so we solve for that. There you go. We substitute everything into the L, cleans it up. Those are the steps we took. We take the derivative, we set it equal to 0. This one is simplifying it and get the numerical value R. And more than that, I made a little table here for the different R values, and clearly the largest amount of light is given at the critical point that we found. You could have also used a second derivative test to check the concavities down. And that would give you that, that's a local max. And that's it. That wraps it up. Beautiful problem, classical. Anybody who is somebody is doing this problem. I hope you guys liked it or enjoyed it or learned something. We'll see you guys on the next one. One more thing I almost forgot is I made this QR code so that you guys can take all the code I wrote here and modify it. If you have to do a different example or if you want to play with the numbers, you can easily just modify it. For example, this portion of it where I wrote the L function or the constraint function. Where was that one? This was the perimeter function, p is equal to 2 pi or 2r h, etc. And then you just click evaluate and you can modify it to your own liking. It's real easy, just point your camera here and it'll take you to the code. All right, that's it. See you guys.